All right, in this video, we're going to talk about section 1.2, dealing with elementary functions, graphs, and transformations. And in this video, we're going to talk about how to perform transformations given the graph of a function, describe transformations on a function and graph the function, find the equations of transformed functions, graph piecewise functions, find equations of transformed functions, and solve applications involving transformations of functions. All right, we're going to begin with some of the basic properties of the 6 elementary functions, and they're going to be very important as we go through this course or in this lesson. The 6 that we'll deal with are the identity function, the square function, the cube function, square root function, cube root function, and absolute value function. And here are illustrations of those 6 basic elementary functions. Okay. Each one of these shows the graph, the range, and domain of each of these functions. Like for the identity function that you see here on the first graph here, the identity function is, of course, f of x is equal to x. F of x equals to x. And the graph of that is a straight line. The domain is going to be the set of all real numbers. The range is also the set of all real numbers. And of course, any x value that you assign to it, you'll always find an f of x value for it. Next is the square function. And that's in the form of f of x is equal to x squared. This is what the graph looks like for the f of x equal x squared function. It's in the shape of a parabola, which we will go into more detail about in chapter 1. And in this case here, your domain is going to be the set of all real numbers, but the range is going to be from 0 to infinity. When it's just f of x equal to x squared, the lowest value for y will be 0, and then it goes up to infinity. So you can see how the graph is opening upward. The cube function, which is f of x equals to x cubed, that's this function here that you see. The domain and the range, of course, are still the set of all real numbers, just like the identity function. And then we have the square root function. That's where f of x, or n of x in this case, is the square root of x. And in this case here, this is what the graph looks like. Notice that it's only going in this direction. It's only defined for only real numbers that are bigger than or equal to 0. So the domain is just going to be all x values greater than or equal to 0. The range, of course, will be all y values greater than or equal to 0, as you can see here. Also, the cube root function, that's the cube root of x. The graph of that looks like this. And in this case here, the domain and the range are going to be the set of all real numbers. And then finally, we have the absolute value function, which is the V-shaped graph. That's what the absolute value function graph looks like. And that's going to be something like g of x equals to the absolute value of x with those absolute value bars. Now, the domain for that is going to be the set of all real numbers, but the range, which is your set of all your y values, the lowest y value, it would ever reach is 0, and it just goes on up like this. So from 0 to infinity would be your range for the absolute value function. All right, so be familiar with those 6 basic elementary functions because we'll be using those throughout this section. All right, now on the next page are transformations, which is what we'll talk about here. When a new function is formed by performing an operation on a given function, the graph of the new function is called a transformation of the graph of the original function. Okay, so the first of these 2 types of transformations that we'll deal with are vertical shifts and horizontal shifts. First, the vertical shift. The graph of y equal f of x plus k gives a vertical transformation of the graph of y equal f of x. Now, if k is positive, that means that the vertical transformation is upward by k units. And of course, if it's negative, then that means your vertical transformation will be downward by K units. So vertical means that the Y is going to be changing because vertical goes up and down. And then when we have the graph of Y equal F of, in parentheses, X plus H, notice here, you're going to get a transformation of the graph of Y equal F of X. Now, if H is positive, then the horizontal transformation is to the left by H units. Now, note that this is going to be the opposite of what you might expect. So with the horizontal transformation, you're going to end up doing the opposite of what's inside the parentheses. If it's a plus H, that means you're going to go to the left H units. Or if it was minus H, then you're going to be going to the right H units. Okay? So with the horizontal transformation, that means you have to do the opposite transformation or the opposite shift. Now, in detail, let's talk about the vertical shift. The graph of Y equal F of X and then plus K can be obtained from the graph of Y equal F of X by vertically translating or shifting the graph of the latter upward K units, if K is positive, and downward the absolute value of K units, if K is negative. So here's just a couple of illustrations of this. Here we've got the graph of F of X equal to the absolute value of X. This is what the graph looks like on the graphing calculator. But let's say we had this transformed graph, G of X equals to the absolute value of X plus 4. In this case here, that graph has shifted up 4 units, as you can see. Now, another example would be the absolute value of F of X equal to X. But this time, let's say G of X is the absolute value of X, and then we have minus 5 on the outside. You can see the difference between the absolute value of F of X and the graph of absolute value of F of X minus 5. This graph has shifted downward vertically 5 units. Okay. Now, as for the horizontal shift, the graph of Y equal F of, in parentheses, X plus H can be obtained from the graph of Y equal F of X by horizontally shifting or horizontally translating the graph of the latter H units to the left if H is positive, and the absolute value of H units if to the right if H is negative. So here's the difference. Let's say we have the absolute value of F of X equals to, well, F of X equal to the absolute value of X. That's this graph here. But now we want to graph G of X equals to the absolute value of X plus 4. As you can see here, this graph is shifted to the left 4 places. Notice the difference here. You would think you would shift to the right, but with a horizontal shift, you're going to be doing the opposite of adding 4, and that's subtracting 4, and that means you're going to shift to the left 4 places horizontally. And also for the absolute value, well, F of X equals to the absolute value of X. That's the same graph, but let's say we have the G of X equals to the absolute value of X minus 5. This time the graph is shifted to the right 5 places horizontally. Okay. All right, so do be familiar with those here. Now here's a summary of the graph's translations, as you can see here. Pretty much a vertical shift will look like this, and then if K is positive, you're going to shift to the right, shift upward K units. If K is negative, that means you're going to shift downward the absolute value of K units. Then for horizontal translation, here your H is inside the parentheses. That means you're going to do the opposite. So if H is positive, you're going to go to the left, shift horizontally to the left K units. If H is negative, you're going to shift to the right absolute value of H units. So do be familiar with that, okay? Right. Now, next we're going to look at the stretches, shrinks, and reflections. Stretches, shrinks, and reflections. The graph of y equal a times f of x, where a is a constant, can be obtained from the graph of y equal f of x by multiplying each ordinate value by the latter by a and graphing the points with these new ordinate values. Like, for example, well, here it is. If a is positive, that means you're going to get a vertical stretch of the graph of y equal f of x. Or if a is a number between 0 and 1, you're going to get a vertical shrink of the graph of y equal f of x. And a equaling to -1, or if a is just negative, then you're going to get a reflection in the graph about the x-axis. Okay, well, we'll just say a is equal to -1. And keep it like that. All right, so in this example, for a vertical stretch, here's the graph of f of x equals to the absolute value of x. Looks like this. Here's g of x equaling to 2 times the absolute value of x. So here we're stretching this graph of absolute value of x by a factor of 2. Now for the vertical shrink, for f of x equaling to the absolute value of x, if we have something like g of x equals to 1/2 or 0.5 times the absolute value of x, that means the graph is going to look like this. So here you have a vertical shrink by a factor of 0.5. Now, let's say we had a graph with a vertical stretch and a reflection. Like, in this case, g of x is equal to -2 times the absolute value of x. Notice that it has shrunk by a factor of, well, stretched vertically by a factor of 2, but it's reflected about the x-axis. Here's the x-axis here. Normally, the absolute value of x will be up here. Now, since it's reflected about the x-axis, it's below the x-axis, okay? Reflection usually has a mirror image. So this is the mirror image of this. And we have a vertical stretch by a factor of 2. All right, so on the next page is a summary of stretching and shrinking. As you can see here, if a is positive for y equal a times f of x, where a is a constant, a is positive, that means you're going to have a vertical vertical stretch. I always get those confused. Vertical stretch by multiplying each ordinate value by a. And then if a is between 0 and 1, that means you have a vertical shrink. And you'll do that by multiplying each ordinate value by a. Okay, now let's talk about reflection. Let's go into more detail about that. Let's say we got f of x equals to the absolute value of x minus 3. So if you were to do this in the calculator, this is what the graph would look like. And then for g of x is equal to the absolute value of x minus 3, here's what that graph looks like. Notice it's a reflection about the y-axis, because here's the y-axis here. We reflected this graph to end up over here. That's when the input value of x is replaced by -x. So it's a reflection about the y-axis. All right, and next is just a summary of the reflections here. Reflection about the x-axis and a reflection about the y-axis. So reflection, which is y equal -f of x, that reflects the graph of y equal f of x in the x-axis. And when you have the negative sign in front of the x, y equal f of -x, that's going to be a reflection about the y-axis. Okay. Now let's look at some examples of this that's similar to the ones that are in your homework in MyMathLab. Now let's say we had this. The graph of y equal f of x is shown in red. Let's say I want to graph y equal f of, and in parentheses, x plus 3. And you want to choose the graph that's shown in blue on the right. The one in red is y equal f of x, as you can see here. The one that's in blue is the one we want to choose for y equal f of x plus 3. Now we have to think about what type of transformation that we have here, because the original graph was y equal f of x. And then we got the plus 3 on the outside. So this tells me I have a vertical shift. And it's a plus 3, so that means that this graph went up 3 places from the original graph. Okay, so the blue graph, in this case, had to be shifted up 3 places. And in this case here, you're going to choose which one is that transformation, where the blue graph is shifted up 3 places. And in this case, if you look at it, it's going to be graph C, because notice, here's the graph that's in red. That's the graph of y equal f of x. Notice the blue graph has shifted up 3 places. So it has to be graph C. Okay, now example 2 is this. Here we got y equal f of, and in parentheses, x minus 6. Here's the graph of y, the graph of f of x. We want to sketch the graph of the function described. And in this case, we're just going to choose which one is it. Now notice here, the minus 6 is on the inside of the parentheses. So this time, we have what they call a horizontal shift. So that means it's been shifted either to the left or to the right 6 places. Well, notice that we have a minus 6 in front, so that means that this graph had to be shifted to the right 6 places. So the horizontal shift went to the right 6 places. So that means we need to pick which one of these represents the graph of this function that's been shifted to the right 6 places. And it looks like graph A would be the one that looks like it's been shifted to the right 6 places. Okay. All right, so graph A would be the best fit for this graph of y equal f of, in parentheses, x minus 6. Okay, here's another example where we got the graph of y equal f of x shown in red, and I want to come up with the graph of y equal negative f of x. Negative f of x. So this time, notice that the negative sign is in front of f of x. So in this case here, that negative in front of f of x means that there is a reflection about the x-axis. Now, had the negative sign been in front of the x, and there would be a reflection about the y-axis. So I need to pick the one that shows the reflection about the x-axis. And by looking at these graphs here, B would not work. Neither would C or D. More than likely, it would have to be graph A. Okay? Because if you look very carefully, this end right here reflected to be up here on this end. This end down here looks like it's reflected up here, and all of this reflected down there. So graph A would be the best one for this one to represent y equal negative f of x. All right, here's example 4. And in this case, we're going to indicate how the graph of g of x equals to negative of the absolute value of x plus 3 is related to the graph of f of x equal to the absolute value of x, which is right here, shown below. And then we're going to sketch the graph of that function. So let's take a look at this right here. We got g of x is equal to negative of the absolute value of x plus 3. Notice the negative sign is in front. The negative sign is in front, so that means that there is a reflection about the x-axis. And I also see something else, the plus 3 inside the absolute value symbol. That means that there is a horizontal shift. Not a vertical shift, horizontal shift. Vertical shift means that the plus 3 would have to be on the outside. Here the plus 3 is on the inside, so that means that there is a horizontal shift. And with that horizontal shift, it says a plus 3. That means we have to do the opposite. We have to go to the left 3. And then for the reflection about the x-axis, that means that the graph will have to be shifted downward. We have to reflect downward here. Okay. Now I've already got a graph of, a blank coordinate grid that I'm using here. So let's see what we can do here. First of all, the order of transformation says here, it's just going to be similar to the order of operations. You take your x value, add 3 to it, and then you take the opposite. That's what we'll do first, the horizontal shift, and then the reflection. That means I'm going to take this graph and move it over to the left 3 places. Okay? So that means that this point right here, let me use a different color, is at the origin 0, 0. So that means here I need to go to the left 1, 2, 3. So that point would be there. And if I draw the graph of that absolute value function, and this might be a little bit difficult here, because I know this point will have to be here, this point will have to be here. Because that point right there is 1, 1. So I need to go to the left 1, 2, 3, which will put it here. And then 1, 1 will be to the left 1, 2, 3. That will put it there. And I'm going to draw just a dotted line because this is just the preliminary of this. Okay. So that's just what that graph looks like. Because I also have to do the reflection about the x-axis. So that means I need to reflect this to be down here. So here's what my final graph will look like. This point will still be on the x-axis, but this point will be reflected downward like this. And this point right here will be reflected downward like this. Okay? So that's the reflection about the x-axis. So here's what the final graph looks like. And it's this one that's in green. This is solid graph right here. That's the one that's reflected downward, okay? Because this graph reflected downward and then it shifted to the left 3 places, okay? So that's pretty much how you graph the function f of x equals to the absolute value of negative of the absolute value of x plus 3. Okay. All right, here's another example. Let's say I want to indicate how the graph of g of x is equal to x plus 1 quantity squared plus 1 is related to the graph of f of x is equal to x squared, shown below. And then sketch the graph of that function. So here's what the graph of f of x is equal to x squared looks like. Okay. And pretty much if you wanted to, you can use ordered pairs for this one. Like for x equals 0, 0 squared will be 0. If x is 1, 1 squared will be 1. Negative 1, x squared will be positive 1. For 2, 2 squared would be 4. And for negative 2, you square that would be 4. Okay? So I have some ordered pairs to work with. Now we're shifting. Now here we got g of x is equal to x plus 1 quantity squared plus 1. Notice the plus 1 on the inside. That tells me I have a horizontal shift. And then I got that plus 1 on the outside of the parentheses. That means I have a vertical shift. So with the horizontal shift, it's a plus 1. That means I need to go to the left 1. The vertical shift means I need to go up 1, because vertical goes up and down. So for each point, I need to go to the left 1 and up 1 to get the final graph of g of x equal to x plus 1 quantity squared plus 1. All right, so let me bring this down to here. So if the point 0, 0 is going to be here, and I'll do this, I'll go ahead and plot the graph of f of x equal to x squared on here. I'm going to draw a dotted line. So for each point, I'm going to go to the left 1 and up 1. So starting with this point right here, I'm going to go to the left 1 and up 1. So that point will be here. For this point, to the left 1 and up 1. For this point, I'll go to the left 1 and up 1. For this point up here, I'll go to the left 1 and up 1. And for this point here, I'm going to go to the left 1 and up 1. So this graph, this solid graph that's in red, represents the graph of the function g of x is equal to x plus 1 quantity squared plus 1. So for each point that I use, I took it to the left 1 and up 1. Okay. All right, example 6. Now let's say the graph here is the result of applying a sequence of transformations to the graph of one of the 6 basic functions. Identify the basic function and describe the transformation vertically, and then write an equation for the graph. Well, by looking at this graph right here, we know that it opens upward like this. So one of our 6 basic functions was the graph of f of x is equal to x squared. Okay. So you're going to have to be familiar with those 6 basic elementary functions that I gave you at the top of this video. Okay. Now notice the vertex, which is down here. By the way, the vertex is the lowest point on the graph. So if I go from the origin, I went to the left 1, 2, and down 1, 2, 3. Okay. As I went to the left 2 and down 3 for this one. So that means that the graph of, let's say, g of x is equal to, now I know I'm going to have an x here and then the square will be on the outside. If I went to the left 2 in this case, if I can see that right here, 1, 2 to the left 2, that means that this 2 had to be a plus 2. Because usually a horizontal shift will have the opposite side. And then I went down 1, 2, 3. So that means minus 3. So that means your g of x function would be x plus 2 quantity squared minus 3. Okay. Here went to the left 2, so we have to use a plus 2, not minus 2. And then down 3. That was the vertical shift. So that means we went down 3, so it has to be minus 3 in this case. Okay. Here's another example similar to that. The graph to the right is the result of applying a sequence of well, not to the right. The graph below it is the result of applying a sequence of transformations to the graph of one of those 6 basic functions. Let's identify the basic function and describe the transformation. Okay. In this case here, let me remove some of this stuff here. This graph looks like a V-shaped graph. And one of those V-shaped graphs is the absolute value function. So has to be absolute value of x for f of x. Okay, so now to find out what we did here in this transformation, let's see, this point is usually at the origin. So that means we had to move to the left 1 and down 1. So that means our g of x, which is what I'm going to call it, is going to be the absolute value of x. Now we moved to the left 1, so that 1 has to be a plus 1. We went down 1, so it has to be minus 1 on the outside. And this will be your equation of the function of g of x. We went to the left 1 and down 1. Okay. Another example would be something like this. Let's say we had this graph. Now, one of the 6 elementary basic functions here, or elementary basic functions here, notice it looks like this. And a graph that looks somewhat like that would be the square root function. So f of x was the square root of x. Now we want to find out what g of x is. If you notice, from one of your 6 basic functions, the square root of x would look somewhat like this going in this direction. Notice it's shifted downward. I mean, it's reflected about the x-axis. And it's going downward like this. So that means it's got to be a negative square root of x. And I notice that there is a horizontal shift. It's shifted to the left 1, 2, 3 places. So underneath the radical, it has to be a plus 3. So that means g of x is equal to the square root of x plus 3. And that graph of f of x equal to x, the square root of x is not drawn to scale. So I'm just showing you what that graph would look like. Okay. Now, what about this one here? Let's identify the basic function. All right, the graph of that would be something like x cubed. So f of x is equal to x cubed. Now, again, you have to be familiar with those 6 basic functions I gave you at the beginning of this video. All right, now let's find out what the transformation here is. Usually, this right here will be at the origin 0, 0. This point is. It's shifted to the right 1 and up 1. So that means g of x would be this. We have an x is shifted to the right 1, so it has to be minus 1. And then up 1 is gone. It's a plus 1. Okay. So g of x will be x minus 1. I'm sorry, not squared. That's a cubic function. This should be cube. Okay. X minus 1 quantity cube plus 1. Because that's the cubic function. All right, now let's look at this example here. The graph of the function g is formed by applying the indicated sequence of transformations to the given function f. Find an equation for the function g and graph g using these dimensions, so -8 to 8 for x and -8 to 8 for the y. And they tell you this, that the graph of f of x equal to the square root of x is shifted down 3 units to the right and 3 units down. I'm sorry, shifted 3 units to the right and 3 units down. We just need to find out what g of x is going to be. Okay, so we know we're going to have a square root in here. If it's shifted to the right 3 units, that means it's got to be x minus 3. And if it's 3 units down, that's got to be a minus 3 on the outside. So that's what g of x will look like. Okay, so I'll just write this here as g of x is equal to the square root of x minus 3 with a minus 3 on the outside. That's a function of g of x. Now, you can type this in the calculator and find out what that graph would look like. So here's what I'm going to do. Okay, let me clear some stuff out that I have here. I'm going to go to y equal to, and I'm going to clear this equation out completely, and type in the square root of x minus 3, then minus 3. So for the square root, I'll do second x squared for the square root. And then get your x by pressing the xt theta n button, minus 3. Use your right arrow key to get out from underneath that radical, and then minus 3. Here's what I'm going to do. I'm going to do zoom and 6 for the standard window. I don't know if you can see this or not, but there we go. But that's what the graph looks like. You can see it's shifted to the right 3 and down 3. So you have to pick the one that's similar to this one from these choices of answers. And in this case, it looks like answer A would be the best one to choose, because as you can see, it has shifted to the right 3 and down 3. Okay. Okay. All right, here's the next example. Similar to this one, here we got the graph of f of x equal to x cubed. It shifted 1 unit to the left and 4 units up. We want to find out what g of x is. So in this case here, my g of x, and this f of x equals to x cubed. So I know I got x in there, and it shifted to the 1 unit to the left. Has to be plus 1. It's got to be the opposite. If it's shifted to the left or to the right, it's going to be the opposite sign. And 4 units up, same sign, plus 4. So that's what g of x is. X plus 1 quantity cube plus 4. Now let's graph this into our calculator. So if I go to y equal 2, let me clear this equation out. X plus 1 quantity cube, I'm going to do left parentheses, get the x by pressing xt theta n on the calculator, plus 1, close parentheses, press your hat key for the exponent, which is that upside down v, and then type in the number 3 for the cube. Use your right arrow key to get out from underneath the exponential part, plus 4. And I'll do zoom 6 for the standard window. And that's what the graph looks like. You can see it's shifted to the left 1 and up 4. So you have to pick the one that looks like it's been shifted to the left 1 and up 4. It looks like it's going to be, in this case, graph D. There's a shifted to the left 1 and up 4, so it's over here somewhere. Has to be D. Okay. All right. So that's all of the transformations of functions that we're going to talk about here. Next thing we'll look at is piecewise defined functions. Piecewise defined functions. Now, those are functions whose definitions involve more than one rule. Graphing one of these functions involves graphing each rule over the appropriate portion of the domain. So here, a piecewise defined absolute value function like f of x equal to the absolute value of x can be written as this. The absolute value of x will be equal to the opposite of x is if x is less than 0, or just positive x if x is greater than or equal to 0. So here the absolute value function is defined by different rules for different parts of its domain and is a piecewise defined function. Okay. And by the way, if I do the absolute value of x on the calculator, so if I go to y equal to, clear this out, for the absolute value, there is a button where I can press, which is the math key on the left-hand side. If I press the math key, go to NUM for the number menu, select number 1 for ABS, which is short for absolute value. Now, in these newer calculators, they give you absolute value bars. And then press xt theta n for your x. And if I want to graph this, I can press the graph key. You'll see it looks like a V-shaped graph. So in this case here, for anything greater than or equal to 0 will be this. Anything less than 0 will look like this on the left-hand side. That's why it looks like it's the V-shaped graph. All right, but let's graph a piecewise function in this example. Let's say we want to graph the function f of x is equal to 3 minus 2x if your x value is less than 1, and x minus 2 if your x value is greater than or equal to 1. So let's start with f of x is equal to 3 minus 2x. Now the restriction here is that your x value is less than 1. I'm going to pick 1 here because I want to find out what it would be when X was equal to 1, because there I'm going to draw what they call a hole in the graph. And let's pick values less than 1, like 0, -1, -2. And then each value will just substitute the X in this function. So if X is 1, 2 times 1 would be 2, 2 from 3 would be 1. And I'm going to put right here this word, the hole, because you're going to have a hole in the graph at the point 1, 1. Now if X is 0, 2 times 0 is 0, 0 from 3 is 3. For -1, minus 2 times a -1 will be 2, 2 plus 3 will be 5. And for -2, minus 2 times a -2 would be a plus 4, 4 plus 3 is 7. Okay, so now we're going to plot this here. At 1, 1, if I go to the left 1 and up 1, that point will have what they call a hole in the graph. Notice I'm drawing a hole in the graph to indicate that that point will not be included in the graph of f of x equal to 3 minus 2x. 0, 3 would be to, we stay at 0, but go up 3. Oh, I'm sorry. This is wrong. To the right 1 and up 1. That's this one right here. That's where the hole in the graph will occur. So disregard this right here. Okay, disregard that. To the right 1 and up 1, that would be the point where the hole in the graph will occur. 0, 3 is here. -1, 5 would be to the left 1 and up 5. And -2, 7 would be to the left 2 and up 7. So this part of the graph looks like this. Now notice I'm not drawing a line through that hole in the graph because that's not included. Okay. Now the other piece is x minus 2 if x is greater than or equal to 1. So a table of values I'm going to use here. Greater than or equal to 1 means 1 will be included, so I use values like 1, 2, and 3 as x values, and then substitute in f of x equal to x minus 2. So like if x is 1, 1 minus 2 would be -1. For x is 2, 2 minus 2, that's going to be 0. For x is 3, 3 minus 2 will be 1. So let's plot those. 1, -1 will be to the right 1 and down 1. 2, 0 to the right 2 and on the x-axis. 3, 1 will be to the right 3 and up 1. So now if I plot those points, here's what that graph looks like. Okay, so that's the graph of the function of this piecewise function for f of x. Okay. All right, next we're going to look at some application problems that are related to piecewise functions, by the way. So let's say the table to the right shows the electricity rates charged by better than lighting utilities in the winter months. Okay. And in this case here, we got 2 parts here. We want to write a piecewise function of the monthly charge labeled W of X for a customer who uses X kilowatt hours in a winter month and determine the graph of W of X. All right, so now here we have this. The base charge is $8. The first 300 kilowatt hours or less is going to be at 0.07 kilowatt hours. Over 300 kilowatt hours will be at 0.0900 kilowatt hours per kilowatt hours. Okay. So here we want a piecewise function. So let's say here from 0 to 300, if X is from 0 to 300, then it's going to be this function here. From 0 to 300, that would be the base, which is $8, plus 0.0700 per kilowatt hour times the number of kilowatt hours. So that would be 0.0700 X. And that means X is the number of kilowatt hours. So this amount per kilowatt hours will be multiplied by X. And in anything over 300, will have to be this. And also I need to write the restriction here if X is between 0 and 300. And anything over 300, and notice that 300 is less than X means X has to be greater than 300. All right, let's do a little bit of scratch work here for this one. The base charge is $8 plus this amount, which will be 0.0900 times anything over 300. So that means X is going to be the number of kilowatt hours minus 300. So now we need to simplify this expression here using the distributive property. If I distribute the 0.0900 over this, in the parentheses, I have 0.0900x minus, and if I do 300 times that 0.0900, I get 27. Okay, I need to correct something here. This is all incorrect here. So this part is correct. $8 for the first, $8 plus 0.0700x if your x is between 0 and 300 inclusive. Now for the other part of that equation, for anything over 300. Okay, let's think about this for a moment here. When a person reaches 300 hours, let's say that that person reaches 300 hours, kilowatt hours, at x equals 300. That means W of 300 would be using this times and replacing that x with 300. So it would be 800 plus 0.0700 times x, which is going to be 300. And if you were to put this in a calculator, and I think I've already done this. I'm going to go ahead and do it again. 800 plus, and in parentheses, 0.0700, 0.0700 times 300, close parentheses. Oops. I'm sorry, that's not, that should be 8 plus 0.0700 times 300. That would be 29. So that means for the first 400 hours, first 300 hours, this person's going to be paying $29 plus. Now, let's say that person goes over 400. That $29 will be included with anything that's over the 400. So that means here, this person will be paying $29 plus any kilowatt hours that are over 400, which is in this case 0.0900 times whatever's over 400. So this would be 0.0900 times x minus anything over 300. Now we need to simplify this expression here. So that means this is going to be 29 plus 0.0900 x minus 0.0900 times 300 would be 27. And 29 minus 27 would be 2. So it'd be 2 plus 0.0900 x. That would be the expression for the other part of that piecewise function. So this one would be 2.00 plus 0.0900 x, and that is if x is greater than 300. So that would be our piecewise function in this case. And now we have to pick which one of these is the correct graph of the function of w of x. Okay. Well, let's look at this for a moment here, because I know at 300, it was what? It was 29, which is close to 30. So that means we have to pick the one that's closest to 30 here. And it kind of looks like answer B, because if I look at the way this graph is sectioned off, it's pretty much a section off in increments of 5, like 5, 10. Well, increments of 5 on this one. So 29 is close to 30, so that would be probably this graph right here, graph B. And the x-axis is section off in hundreds. So it's like 100, 200, 300. That would be like 29. And then the graph looks the rest. Okay. So pretty much you have to look at your x and your y-axis to see how it's sectioned off. Okay. And finally, example number 14 deals with tax returns. Okay. Now here the table below shows a recent state income tax schedule for individuals filing a return. This one is for single-head household or married filed separate. And there you see the table, what it looks like for your taxable income. Now here we want to write a piecewise definition of the tax due or T of X on income of X dollars. All right, in this case here, we're going to start with the first row from $0 to $15,000. The tax due will be 4% of your total taxable income. Well, that one's going to be easy to write because of the fact that we're just only going to take 4% of your taxable income. So that means T of X will be, now 4% as a decimal will have to be 0.04 times, and we're letting X be your taxable income, so it'll be 0.04 times X. That's the first piece. Now the restriction on that would have to be from 0 to 15,000. That is, if X is between 0 and 15,000. course, we'll put the equal sign underneath that, less than or equal to. Now, the next one is this. If it's over 15,000, but not over 30,000, it's going to be the $600 plus 5.5% of the excess over $15,000. Here they give you the amount plus the amount over 15,000. So, which is, in this case, we can just write the piecewise function as this. Now we're going to have to do a little bit of algebra at the bottom. So here I'm going to use a separate sheet of paper. In this case, because that's going to be 600 plus 5.5% as a decimal will be 0.055 times x minus the amount over $15,000. So the x minus 15,000. Now let's do some algebra here. Here I got 600 plus 0.055 times x will be 0.055 x minus 0.055 times 15,000. If you do that in the calculator, you'll get 825. And then subtract 825 from 600, that would be negative 225 plus 0.055 x. So this expression here we will use for values that are over 15,000 but less than 30,000. So this will be negative 225 plus 0.055. That's if, and of course they already give this to us, 15,000 is less than x, less than or equal to 30,000. And then for the last one, 30,000 on up would be 1425 plus 6.8% of the excess over 30,000. So in this case here, we'll just write that as an algebraic expression, 1425 plus 6.8% would be 0.068 of the amount over 30,000, x minus 30,000. Now, if we distribute this, simplify this, this will be 1425 plus 0.068 times x will be 0.068 minus 0.068 times 30,000 will end up being, on the calculator, 2,040. 1425 minus 2,040 would be negative 615 plus 0.068 x. So that's going to be the third piece here. Negative 615 plus 0.068 times x. That's if, let's say 30,000 is less than x, which is the same as saying x is greater than 30,000. Okay. Now, part B is determining the graph of T of x. I'm going to eliminate part B in the homework, but actually it would be answer B for that. But part C says this: find the tax due on taxable income if of $28,101. So using that piecewise function, we got to find out which one of these we need to use for the taxable income based on this amount, $28,181. That falls between 15,000 and 30,000. So we need to use negative 225 plus 0.055 x for our taxable income. So T of 28,181 is going to be this: negative 225 plus 0.055 times x, which is 28,181. And if we type this into our calculator for our final answer, negative 225 plus 0.055 times 28,181. That would give us, to two decimal places, $1,324.96. So this will represent the tax due on taxable income of $28,181. Okay. All right, so that does conclude this video on section 1.2, dealing with elementary functions and graphs and transformations. Feel free to reach out to me if you have any questions about anything that's been presented in this video or any of the homework problems that are in my math lab.